Okay, hello. Welcome to the last interactive session for this course on fluid and particle mechanics offered this semester on NPTEL by Professor Sumesh and Professor Basaraj. I'm Shankar. I'll be your teaching assistant for today. As I mentioned, this will be the last class for this course offered this semester. And the exam will be as per the schedule that is given on the SWAM website. So I request you to take a look at that. If you have any doubts, please get back to me or write to the NPTEL website. Okay, let's. This session will have contain all the questions from week 12, the graded and non-graded ones, and then we'll move on to an overall summary of the entire syllabus. We'll go through whatever that was taught in week 1 to week 12, and finally we'll wrap it up after with a complete summary of whatever we've learned. So let's get started with the first question. In the week 12, we are doing questions on boundary layer and phenomena associated with that. So let's first take a look at this question on for the flow of sea level standard air, where the density is given out to be 1 kilogram per meter cube. Kinematic viscosity is given as 1.5 into 10 raised to minus 5 meters square per second at a velocity of 10 meters per second parallel to a flat bed. Now, what is asked is the Reynolds number at a distance 10 centimeter from the leading edge. So what is given is there is the seabed sea interface, sea air interface, so that is there, and there is flow of air in one direction going at 10 meters per second. We just have to find the Reynolds number 10 centimeters from the leading edge, assuming that it starts from either land or it starts from land. So let us consider the formula for Reynolds number, which is rho Vd by mu, also given as Vd by nu, where nu is the kinematic viscosity, and kinematic viscosity is given as 1.5 into 10 raised to minus 5 meters square per second, and the velocity is given as 10 meters per second. Now, since this is a flat plate problem, we have to consider the Reynolds number defined as Rex, where x is the distance from the leading edge. So we have to consider Vx by nu, and therefore we substitute the values of x as 0.1 or 10 centimeter, which is basically 0.1 meter. So let's take a look at what the Reynolds number we find here. It will be 10 into 0.1 by 1.5 into 10 raised to minus 5. We'll get this value as 66,666.67. So for a flat plate, the critical we'll just go over what would be the critical Reynolds number for a flat plate. Just Google it out. We see that for a flow along a flat plate, the critical Reynolds number is 500,000. So it is safe to assume that a value that is 66,000 is in fact a laminar flow. And the reason why this is important comes up in the next question, where the boundary layer thickness at a distance of 10 centimeter from the leading edge is asked. And for that, the formula varies depending on which regime you are in, whether in the laminar flow regime or the turbulent flow regime. And for the laminar flow regime, what we have is an equation that is given as delta by x equal to 5 by square root of Rex, and where delta is the boundary layer thickness. So we'll get this as 5x by square root of rex, and what we found out was 5 into 0.1 by square root of 66,667. This answer will come out to be equal to 0.19 in the unit of centimeters. So I'll give you a minute if you need to catch up, and then we'll move forward with the next question. Okay, we'll move on to the next question now. Question number 3. We have to calculate the wall shear stress at a distance of 45 centimeters from the leading edge. So we know that from the classes you would have already learned that the wall stress formula is 2W is equal to 2 mu u infinity by delta. All the values are given directly, you just have to substitute them. But kinematic viscosity is given, which is nu, which is equal to mu by rho. Therefore, mu is equal to the density times the kinematic viscosity, which is 1 kilogram per meter cube times 1.5 into 10 raised to minus 5 meter square per second, which will effectively be numerically equal to the same as kinematic viscosity. All right, so finding the value of the shear stress, we'll get 2 times 1.5 into 10 raised to minus 5 times u infinity, which is 10 meter per second divided by delta, which we just found out to be 0.19 centimeters, which is 0.0019 here. Okay, this value will come out to be 0.157 Pascal. I'll give you all a minute to catch up, and then we'll move on to the next question. Okay, I hope everyone you got the answer now. We'll move on to a set of true or false questions and find out the answers for these particular questions. Yeah. So, for the question number four states for the uniform flow past a flat plate, the boundary layer exists because the flow has to respect the no slip boundary condition on the surface of the plate. That statement true or false? So it states that for a flow past a flat plate, there exists a boundary layer such as this because, sorry, there exists a boundary layer such as this because the flow has to respect the no slip condition on the surface of the blade, and that statement is true. The no slip condition on the surface of the plate creates a viscous effect which causes the velocity to die down as it approaches the wall or the plate. Next, question number five. The momentum thickness in the Karman's analysis of flat plate is defined as theta equal to integral 0 to delta u by u into 1 minus u by u dy, where capital U will be defined as the free stream velocity or the bulk velocity, and small u is the velocity profile at which we are concerned about. From the discussion we had in class, this was what we have defined as the momentum thickness. There is a boundary layer thickness, there is a momentum thickness, and there is also a displacement thickness. And the momentum thickness described here in over here in the Karman's analysis of the flat plate such as this is the correct answer. So therefore this is a true statement. Okay, now let's look at question number 6. The drag force on the plate is related to the momentum thickness dx is related to the momentum thickness theta, as d of x is proportional to 1 by theta. Dx is inversely related to theta. Now, is that statement is true or false? It is actually false, because from the lecture it was told that, or it was mentioned that the drag force is basically given by d is equal to rho b u infinity square times theta, or d by rho b u infinity square is equal to theta. Therefore, we can see that there is a direct relation between the momentum thickness and the drag force. Question number 7. The skin friction coefficient in a flat plate boundary layer calculation is analogous to friction factor in flow through ducts. So the skin friction coefficient in a flat plate boundary layer is basically coming as a result of the presence of a no slip condition on the plate, and the friction factor is coming up as a result of the friction on the ducts, and that has been caused due to the roughness over there. So this statement is in fact true, where both of them is retarding the velocity profile and providing a zero or a no slip condition at the boundary. Now, question number 8. The local Reynolds number of a boundary layer does not change with the leading edge. We know that the Reynolds number for a flat plate is given by rho v x by mu, and this x refers to the distance from the leading edge. So, as you can obviously see, the statement will in fact be false. Okay, we'll move on to question number 9. The displacement thickness is always equal to the boundary layer thickness. That statement from the lectures given, if you remember it, the momentum thickness, or the displacement thickness, sorry, which is given by delta star, uh, is related to the is later as 1.83 times root of Rex. Sorry, this is delta star by x, and the displacement, sorry, the overall boundary layer thickness is given by delta by x is equal to 5 by square root of Rex. As you can see, the displacement thickness is not equal to the boundary layer thickness and is in fact smaller than the boundary layer thickness. So again, this statement is false. Okay, question number 10. The boundary layer can either be laminar or turbulent. And when the discussion was going on in class, the Reynolds number was, although taken into account over here, it was the boundary layer. We never spoke about the flow or the condition in which the flow occurs through the boundary layer, and therefore the boundary layer can be either laminar or turbulent. This statement is therefore true. Okay. Next question. The displacement thickness can be calculated as delta star is equal to integral 0 to delta 1 minus u by u d by. This is directly from the class, and yes, the statement is correct. Okay, question number 12. The ratio of displacement thickness to the boundary layer thickness varies only with the dimensionless velocity profile u by u. So as you can see, we have written down the equation for the displacement thickness, and this is the equation for boundary layer thickness. So if we divide the displacement thickness to the boundary layer thickness, we will not get anything. Basically, will be dimensionally delta star by delta will be just 1.83 by 5 for the laminar region. And for the turbulent region, again, more analysis would be required. But we can safely say that this statement is false since there is no velocity profile coming up. And the last true or false question, the wall stress near a flat plate boundary layer tau w is proportional to d theta by dx d whole square, where theta is the moment of thickness. Now that statement does not is actually false. I'll choose the answer first because the explanation is like this: the drag force is actually given by d by rho b u infinity square. This is given by theta. Now we equated this to differentiated this as dd by dx as rho b u infinity square times d theta by dx. And we said that dd by dx is in fact the shear stress at the wall times the width. Therefore, we can find the shear stress at the wall to be equal to rho u infinity square times d theta by dx. So what we are seeing is tau w is proportional to d theta by dx. So this square is incorrect. So I'll give you a minute. If you have any questions, please feel free to let me know. So I'll just wait for a couple of minutes for you guys to catch up. Okay. Is there no more questions? We'll move on to question number 14, where air at 20 degrees Celsius and 1 atmosphere, the density and viscosity is given, enters as 40 centimeter square duct as shown in um, figure 1, where this is a square duct of length 40 centimeters. And using the concept of displacement thickness, we have to estimate the Reynolds number at position 1 meter away from the entrance. So the Reynolds number is given by rho Vx by mu. Rho here, let's write down the values of rho to be equal to 1.5 kilogram per meter cube. Viscosity to be equal to 1.5 into 10 raised to minus 5 Pascal seconds. Velocity to be equal to 2 meters per second, that is given here, and the position to be equal to 1 meter. Therefore the Reynolds number is equal to 1.5 into 2 into 1 by 1.5 into 10 raised to minus 5. Which should give the value 200,000. Okay, now we have been asked to find the boundary layer thickness at a position 1 meter away from the entrance, and we see that the Reynolds number corresponds to a value of 200,000, which means that this is still in the laminar regime. As we saw earlier, 500,000 was the critical Reynolds number value. So therefore, the boundary layer thickness 1 meter away from the value or away from the entrance will be given by solving this. Delta by x is equal to 5x by root of Rex, and where x is equal to 1 meter. Therefore, delta is equal to 5 by square root of 200,000. which is basically 0.11 meter or 11 centimeters. Now we have to find the displacement thickness at a position 1 meter away from the center, which is given by delta star by x, which is 1.83 x by square root of rex. There's no x here, sorry. Okay, there is no x here. And this is equal to 1.83. Okay, wait. We can find delta star from this, which is 1.83 times 1 by square root of 200,000. And you'll get the answer as 0.00409 meters. I forgot to write meters. Yeah, I did write that. Okay. Which is basically 4.4 centimeters. Now we have to find the total flow rate through the pipe, which is nothing but V bar times area. V bar is the average velocity or the entrance link velocity, which is, sorry, 4, it is 2 meters per second times the area for a square duct is given by a square, and the area is equal to a square, and a is equal to 0. It's 40 centimeters, which is 0.4 meters, which will get the 0.32 meter cube per second. Okay, I'm gonna leave these two questions, the mean velocity in the core of the flow and the average pressure gradient, to you, because I think it's quite straightforward. Again, you just have to solve a couple of equations, and we'll move on to question numbers 20 to 26. In the interest of time, I'll be skipping forward a little bit faster. So yeah, now you have to identify what these numbers are, or what these letters stand for, as corresponding to the right hand side of the column. So we see that there is a solid object that is given here, and there is an initial boundary layer, then followed by another boundary layer, and we know that the first boundary layer is called as the laminar boundary layer, and the one after that, where delta is much less than L, entrance length is much less than L, will be the turbulent boundary layer. So the correct answer I am writing on the left side will be equal to A1 B2, because the first is the laminar region followed by the turbulent region over here. Now if you look at C and D, what you can see is this is in fact the free stream velocity capital U, whereas there is a velocity profile which is indicated by small u, and we know that the free stream velocity will always be larger than the velocity profile at the near the solid wall or solid plate. Therefore, the option C would correspond to the free stream velocity capital U, and option D would correspond to the velocity profile small u, which is less than u. Now taking a look at E and F, we know that whatever is inside will follow a laminar path, or this is inside this boundary layer, and whatever here will be completely turbulent, and that is characterized by the inviscid flow at F and viscous flow at E. So therefore correct answers would be E5 and F6. Okay, if you have any doubts, please do let me know. We'll I just written down the same question here. Okay, I'll just do 3 questions from this and stop, and then go to the summary, because for from 26 to 33 is just a repetition of whatever we have learned. So first we have to identify for a flow past a thin plate at 20 meter per second, estimated the distance x from is the leading edge at which the boundary layer thickness will be 1 millimeter or 10 centimeter for air and water. So there are 6 questions or 9 questions in total. It's very straightforward. I'll just do the first 3 and then we'll let you know. I'll hope you'll be able to figure it out. So first we have to find out the distance x at which the boundary layer thickness will be 1 millimeter. And so for that all you have to use is find the delta by x is equal to 5 by square root rex. Here the only variable we have to find is the x. And we have to assume that the density is 1.5 kilograms per meter cube and the viscosity to be 1 into 10 raised to minus 5 meters square per second of that sort. Then if you solve this, if delta s is equal to 1 millimeter, we'll get x to be equal to, I got the answer as 0.0533. And the Reynolds number corresponding to this will be just 1.5 into 20 into 0.0533 by 1.5 into 10 raised to minus 5. This will be 71,111, indicating that this is a laminar regime. So how you solve this question is, since you don't know whether it's in a laminar regime or not, you find the distance from the leading edge at which the boundary layer thickness comes out. If it is in the laminar regime, just go with it. Otherwise, you have to resolve the question considering the turbulent flow. So let's do this question and maybe it will be clearer here. So first we solve by using delta by x is equal to 5 by square root rex. And we use everything as given except for the fact that delta is 10 centimeter now, which is 0.1 meter. And we'll get a value for x. And if you substitute that value in the Reynolds number, let's call that as x1 or XL, indicating laminar flow. If we calculate the value of REXL, you'll find that the Reynolds number will be of the order of 8.6 into 10 raised to 7. So therefore, we need to redo this question and considering the turbulent flow, which is given by delta by x is equal to 0.379x by square root of Rex. There's an x over here, sorry. And if you do that, you will get a value again that is very close to 8.6 into 10 raised to 7. So that's how you figure out whether you find the solution in the laminar regime or the turbulent regime. Okay, I thought I muted myself. Thank you. So I think I'll stop here with the solution. I think the rest of them just 4 more questions. Just do this for water, and we have. I'll just do this as well, where we have 3 more true or false statements. This is from the practice problems or the non-graded assignments in of week 12. So question number 3 is, when a boundary layer with adverse pressure gradient. If you remember from the class, we had a pressure gradient. That means the pressure increases in the flow of in the flow direction. dP by dx is greater than 0, and the point of inflection can be at the surface of the plate. So That statement cannot be true since we always saw that there is some deviation over here that's happening depending on the magnitude of the pressure gradient. So this statement is false. Next, Karman's momentum and integral analysis or in estimate is equally true for turbulent boundary layers as for laminar boundary layers. But the analysis will fail if the plate is rough. That statement will be false because Karman's momentum integral analysis is there for both turbulent and boundary layers, and it will stay true even if the plate is rough. Next, laminar boundary layers separate faster than turbulent boundary layers, though turbulent boundary layers are thinner than laminar boundary layers. And yes, that is obtained from these equations. Also, we can see that the turbulent boundary layers are thinner than laminar boundary layers, but the leading edge up to which the boundary layers have are shorter for laminar boundary layers. So this statement will be true. So I'll give you all a couple of minutes to go through what we have learned. After that, I'll give you a smart 15-minute, 20-minute summary of whatever you learned from week 1 to week 12 and in the class after that. Okay, let's recap whatever you learned. So I have all the lectures from week 1 onwards over here. Yeah. So this was literally the first assignment we had done, and yes, you can see we've written a lot of them. So first was regarding fluid statics, Newton's law of viscosity, and equation of continuity in Cartesian coordinates, and equation of linear momentum in Cartesian coordinates. We saw how to use the mercury manometer, the pressure gauge, how to calculate the pressure, differential pressure, how to do if a tank is given, which is divided into two parts, a reservoir is given, and we also saw how to satisfy the continuity equation in the Cartesian coordinates, uh, and the Navier-Stokes equation as well. So that was it for the first week. If we move on to the second week, we have, oh sorry, this may not be the lecture. Just a second. Oh, I may not have week 2 and week 3. In fact, I'll have it in my system. Yeah, I can see here, over here. So, yeah. So week 2 was related to, again, continuing on the we did week 1 problems then, and week 2 was on Bernoulli's equation, solution of continuity in the cylindrical coordinates, and solution of Navier-Stokes equation in the Cartesian and cylindrical coordinates. We saw many questions based on that. We saw how we can develop a question based on this and formulate and find the answer from these measurements. So let me go to the SWAM website and I can show you there itself. It will be easier if we do that way. So yeah, for the last semester I was the TA for computational fluid dynamics. So yeah, I have that going on as well. And for this semester I'll be the TA for the fluid and particle mechanics course. So exam date is given as 28th of October, and I think according to the hall ticket that will change given to you. And once we finish week 3, we have gone to week 2. We have gone, sorry, once we finished week 2, we have gone to week 3, where it was on circular Poiseuille flow, shear stress distribution, circular Taylor flow, and Couette flow, viscosity and momentum transfer, many devices which are discussed by Professor Basavaraj, fluid properties and its behavior, and rheological measurements based on that. So that's what we've been dealing with in week 3. Moving on to week 4, we had the non-dimensional analysis, where we tried to equate the dimensionality and thereby find the answer based on that. Dimensionless numbers such as Stanton number, Prandtl number, Reynolds number has been discussed here. And scaling analysis was discussed towards the end of week 4. Week 5 saw complete Buckingham Pi theorem, the Trinity test, which discussed the atomic blast happened in World War II, the concept of similarity, and some colloidal particle systems, characterization of particles using their shape, sphericity, etc. And the motion of particles in a fluid, the Brownian motion, and the electrophoresis, etc. So we discussed that as well over there. And yeah, those are some of the topics we had discussed. And yeah, the specific surface area, which is given by the surface area per weight. Now, week 6, we discussed about sedimentation, separation, settling velocity, Stokes regime, Newton's regime, and aggregates of colloidal aggregates. We had a small section on question on fractal dimension, which we had discussed in great detail. And yeah, those were the we discussed the parameter K, which was there. which determined which regime it was settling, the particle was settling in. In week 7, we still continued with the colloidal free settling and the hindered settling velocity. After that, we went through the flow through a packed bed and its pressure drop associated with the packed bed, which we discussed the Ergun equation, the Korsny-Karman equation, and the Burke-Plummer equation in great detail in this week. In week 8, we continued the pressure drop through the packed bed, and we discussed fluidized bed reactor and filtration, the cake filtration, and constant pressure filtration and constant flow rate filtration are the two things we had discussed here. And these were discussed in great detail as well. In week 9, we were focusing on the laminar and turbulent flows, and we started with laminar turbulence flows from week 9, and we moved on and continued that discussion until here. And we discussed the average concept of average velocity, the core, the inviscid core, and the turbulent boundary layer, etc. over here. And the concept of average velocity and deviational velocities, which is given by y dash, came up in the context of turbulent flows. Now, in week 10, we discussed the effect of roughness in pipes, the friction factors, Fanning and Darcy's friction factors, how to calculate them from Moody's chart, and pipes of non-circular cross-section, where we found out the characteristic length, the minor losses, sudden expansion and contraction, and the frictional losses in a pipe, etc. The head loss, the overall head loss, the roughness ratio, and how to calculate them from the table. And we had discussed one of the longest assignments ever, which is 43 questions in this one. In the previous, in the last two previous, that is in the week 11, we had discussed questions on momentum and kinetic energy correction factor alpha and beta, which connects through to the Bernoulli's equation, which is applied in the Bernoulli's equation. The pressure drop in which the pipe conduction are parallel and series connection, which is similar to or analogous to the electricity or the circuit diagrams that were discussed in the context of electrical engineering, where you have series and parallel connection, and how the pressure drop remains the same at parallel connection, and how the flow rate remains the same in series connection. In the last week, which we discussed today, we were talking about the boundary layer, then the analysis. Boundary layer momentum thickness, the displacement thickness, and the boundary layer thickness, and all the factors associated with that. Now, among all of this, there were through these 12-week course, we have given a full overview of the fluid and particle mechanics as been discussed. And yeah, if you have any questions, please let me know. I think I'll stop here for now. I would like to thank you for your time and attention. I hope I have done a reasonably good enough job to satisfy the questions that you had, satisfy the answers that I've given you. I sincerely thank you. I sincerely thank you for your time and attention. Hope you have an easy exam that you'll be attempting, and wish you the best of luck. Thank you.